The process of measuring the complexity of algorithms is called the analysis of algorithms. We will concentrate on the time complexity of algorithms, because it is usually more important than the space complexity in this video. As I said, the analysis of algorithms is the process of measuring the complexity of algorithms. Your measure of the complexity of an algorithm should be easy to compute, certainly easier than implementing the algorithm. You should express this measure in terms of the size of the problem. This problem size is the number of items that an algorithm processes. For example, if you are searching a collection of data, the problem size is the number of items in the collection. Such a measure enables you to compare the relative cost of algorithms as a function of the size of the problem. Typically, we are interested in large problems. A small problem is likely to take little time, even if the algorithm is inefficient. Realize that you cannot compute the actual time requirement of an algorithm. After all, you have not implemented the algorithm in Java and you have not chosen the computer. Instead, you find the number of operations for the problem size that behaves like the algorithm's actual time requirement. However, we do not need to count all operations to solve the problem. The operation that we need to consider is called a basic operation. An algorithm's basic operation is the most significant contributor to its total time requirement. For example, algorithms A, B, and C in the previous example have addition as their basic operation. An algorithm that sees whether an array contains a particular object has comparison as its basic operation. Realize that the most frequent operation is not necessarily the basic operation. For example, assignments are often the most frequent operation in an algorithm, but they rarely are basic. Ignoring operations that are not basic, such as initializations of variables, the operations that control loops, and so on, will not affect our final conclusion about algorithm speed. For example, algorithm A requires n additions of I to some in the body of the loop. We can conclude that algorithm A requires time that increases linearly with n, even though we ignored operations that are not basic to the algorithm. Therefore, as the number of necessary basic operations increases by some factor such as the problem size, the function of the number of necessary basic operations is said to be directly related to the time requirement. Such a function is called a growth rate function because it measures how an algorithm's time requirement grows as the problem size grows. Because they measure time requirements, growth rate functions have positive values. By comparing the growth rate functions of two algorithms, you can see whether one algorithm is faster than the other for large size problems. Now let's count the number of basic operations required by algorithm C. The basic operations for algorithm C are addition, multiplication, and division. Remember, these counts do not include assignments and the operations that control the loops. The sum of addition, multiplication, and division in algorithm C is 3, and the number is not changed even if n becomes larger. Therefore, the growth rate function, t, n, of algorithm C is 3, a constant. Therefore, we call this kind of algorithm constant algorithm. Now let's move to algorithms A. Algorithm A computes the sum 0 plus 1 plus 2 plus n from left to right. This logic requires an assignment to I, n plus 1 comparisons between I and n additions to I, and n more assignments to I. In total, the loop control logic requires n plus 1 assignments, n plus 1 comparisons, and n additions. Furthermore, algorithm A requires for its initialization and loop body another n plus 1 assignments and n additions. Altogether, algorithm A requires 2n plus 2 assignments, 2n additions, and n plus 1 comparisons. This logic requires an assignment to I, n plus 1 comparisons between I and n additions to I, and n more assignments to I. In total, the loop control logic requires n plus 1 assignments, n plus 1 comparisons, and n additions. Furthermore, algorithm A requires for its initialization and loop body another n+1 assignments and n additions. Altogether, algorithm A requires 2n+2 assignments, 2n additions, and n+1 comparisons. Generally, the equals are not included in the basic operation, so the basic operation for algorithm A is just the addition of sum equals sum plus 1. Therefore, the number of basic operations increases by 1 as the number n increase by 1. In other words, the growth rate function, t, n, of algorithm A is n, that is, it is in the direct proportion to n. We call this kind of algorithm a linear algorithm. The final algorithm we will analyze is algorithm B. The basic operation for algorithm B is also addition. Algorithm B computes 0 plus 1 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 plus 1. Remember, these counts do not include assignments and the operations that control the loops. Algorithm B contains nested loops, for statement for index I and index j. When loops are nested, you examine the innermost loop first. Here, the body of the inner loop requires a constant amount of execution time, and so it is constant. If we again represent that time with an icon, a row of I icons represents the time requirement for the inner loop. Since the inner loop is the body of the outer loop, it executes n times. That is, 1 plus 2 plus n equals n times, n plus 1, divided by 2, which is a half of n squared plus a half of n. Thus, the computation is proportional n squared. The left table summarizes the number of basic operations that algorithms A, B, and C require. The right graph plots these time requirements as a function of n. You can see from this figure that as n grows, algorithm B requires the most time. Typical growth rate functions are algebraically simple. Why? Recall that since you are not likely to notice the effect of an inefficient algorithm when the problem is small, you should focus on large problems. Thus, if we care only about large values of n when comparing the algorithms, we can consider only the dominant term in each growth rate function. For example, n squared plus n, divided by 2 behaves like n squared when n is large. First, n squared is much larger than n for large values of n, so, n squared plus n, divided by 2 behaves like n squared divided by 2. Moreover, n squared divided by 2 behaves like n squared when n is large. In other words, for large n, the difference between the value of n squared plus n, divided by 2 and that of n squared is relatively small and can be ignored. So instead of using n squared plus n, divided by 2 as algorithm B's growth rate function, we can use n squared, the term with the largest exponent, and say that algorithm B requires time proportional to n squared. On the other hand, algorithm C requires time that is independent of n, and we saw earlier that algorithm A requires time proportional to n. We conclude that algorithm C is the fastest and algorithm B is the slowest. The relative magnitudes of common growth rate functions. The growth rate functions that you are likely to encounter grow in magnitude as follows when n is larger than 10. 1 is smaller than log n, which is smaller than log n, which is smaller than log 2n, which is smaller than n, which is smaller than n log n, which is smaller than n squared, which is smaller than the cube of n, which is smaller than 2 to the power of n, which is smaller than n factorial. The logarithms given here are base 2. As you will see later, in the choice of base does not matter. This tabulates the magnitudes of these functions for increasing the values of the problem size n. From this data, you can see that algorithm whose growth rate functions are log n takes much less time than algorithms whose growth rate function is n. Although the value of n log n is significantly larger than n, either of those functions describes a growth rate that is markedly faster than n squared. If the time requirement for an algorithm increase like log n, we call it logarithmic algorithm. If the time requirements are n and n squared, we call them linear algorithm and quadratic algorithm, respectively. The slowest f(n) in this table is exponential algorithm. If the dominant term of a function is a constant power of n, we call it a polynomial time algorithm. A polynomial time algorithm is an algorithm whose execution time is either given by a polynomial on the size of the input, or can be bounded by such a polynomial. Problems that can be solved by a polynomial time algorithm are called tractable problems.